Hello everyone, today we're going to talk about element number 14, silicon. Silicon is a semi-metal and it's a semiconductor on the periodic table with 14 protons and varying numbers of neutrons. We will discuss its varying properties, its varying oxides, and its various compounds that we use it for in everyday life. So let's begin. Focus on silicon. The semi-metal can be used to make hard and soft materials. Sandpaper is made from a compound of silicon and carbon called carborundum. These cupcake liners containing silicon can be put in an oven as they are heat-proof. Silica gel packets are added to dry food, clothes, and shoes to absorb moisture, which is very useful. We even find them in beef jerky. Here's an image of a silicon chip. We will discuss how it's made specifically and its various properties shortly. People that work with silicon need to be even cleaner and have less dust than even those in operating tables, such as those surgeons that are required to wear those masks and gloves to ensure that their patient doesn't get ill, because that's how diseases are transmitted when an individual is not cautious with the dust and the bacteria that they transmit from their bodies. So that's why these individuals are dressed up in this way. It's because they have a strict dress code in these environments. If exposed to any dust or debris, the silicon chip will be ruined and will not work and the computer won't function. So that's why it's important that these conditions be so clean. We'll talk more about that in detail as we continue in the video. So here we go. Silicon, element number 14, again with 14 protons. It's a metalloid. Here's its electron configuration and the average mass of all of the isotopes combined. We previously talked about p-type semiconductors and n-type semiconductors in the boron episode, and in the phosphorus episode we'll talk about them continuously as we discuss other semi-metals on the periodic table. So here we have a p-type semiconductor and an n-type semiconductor. A photon is emitted by excited atom. A photon is just a unit of light. It's a little packet of light that travels at the speed of light, which is 299,792,458 meters per second. Again, the speed of a photon is 299,792,458 meters per second. And that's how fast the photons move. This is an example of silicon usage with the usage of other elements such as boron, germanium, or even arsenic or phosphorus, because they have varying numbers of outer valence electrons that can be used to cause a varying potential difference between these two elements and therefore be utilized to create a switch or an electric flow, or in this case photons that are excited and are emitted, in which case we use to create a laser. We will discuss silicon's various properties for that use and case. So silicon, element number 14. My beguiling charm make computers run and power the digital age. Combined with boron or phosphorus, I am a semiconductor sorcerer. These special powers gave birth to the silicon chip and the computer age. Silicon Valley in California is named after me. I take many different forms. As the second most abundant element on Earth, I crop up in sand, quartz, flint, and countless other minerals. As silicon, a long chain made up of oxygen and organic chemicals. I'm in lubricants, adhesives, and body implants. In glass, I'm perfectly clear. In quartz, watches, and clocks, I keep time, while as silica gel, I ensure that products are moisture free. You'll find me inside sachets packed inside boxes of electrical goods. The date of discovery of silicon is 1824. Its density is 2.330 grams per centimeters cubed. Its melting point is 1,414 degrees Celsius or 2,577 degrees Fahrenheit. Its boiling point is 2,900 degrees Celsius or 5,225 degrees Fahrenheit. Here is a sample of amphibolite. Amphibolite is formed by moderate heat and varying pressure deep in the crust. This coarse-grained rock has an abundance of hornblende and plagioclase, as well as other minerals. So the minerals that are found in amphibolite are magnesium, silicon, oxygen, and hydrogen. In another video, we previously talked about oxygen and hydrogen. We're currently talking about the element silicon, and in a future video, we'll talk about the element magnesium. The elements found in amphibolite are found in the ratios of 7 parts magnesium, 8 parts silicon, 22 parts oxygen, and 2 parts hydroxide, which consists of a repetitive oxygen. So here we go. Silicon. After oxygen, this semi-metal is the second most common element in Earth's rocks. Compounds of oxygen and silicon are called silicates, and there are hundreds of different types. Around 90% of all minerals inside rocks are silicates. The shiny surface of opal is from microscopic silicate crystals. The atomic mass of opal is 28.085. The state is solid. Its discovery is 1824. Baron Johns Jacob Berzelius. So let's continue with the element silicon. So silicon silicon carbides are important abrasives and are used in lasers. The word laser is an acronym. It stands for light amplification by stimulated emission of radiation. So silicon carbide, also known as carborundum, is a semiconductor containing silicon and carbon. It occurs in nature as the extremely rare mineral moissanite. Synthetic silicon carbide powder has been mass-produced since 1893 for use as an abrasive. Silicon carbide, SiC, its density is 3.21 grams per centimeters cubed. Its melting point is 4,946 degrees Fahrenheit, and in Celsius, it's 2,730. Its molar mass is 40.11 grams per mole. Continuing on, an alloy is a mixture of a metal with tiny amounts of other metals or nonmetals. Alloys can be more useful than the pure metals they are made of because they have new and useful properties. Bronze, an alloy of copper and tin, is much stronger than either of pure metals alone. Magnesium silicon alloys, bicycle frames, are made of an aluminum alloy with combined magnesium and silicon that make them very light and strong. So the next time you ride a bicycle, a common bicycle, just remember that it's made of silicon and magnesium. We'll talk about magnesium in a future video. We're currently talking about the element silicon. So the bike frames are made of two metals, magnesium and silicon. Silicon being a semiconductor and magnesium belonging to the alkali earth metals. We'll eventually talk about that element in a future video. So silicon as silicate is present in pottery, enamels, and high temperature ceramics. Here we can see pottery, high temperature ceramics, such as in automobiles which run at high temperatures, or other machinery that require heat resistant materials such as silicon and carbon, which are able to resist high temperatures without melting while still allowing the machine to work and function as needed. So here are the enamels that are produced by silicon. So silicon alkyd high heating coating. Silicon dioxide is one of the various oxides that silicon forms. It occurs when oxygen oxidizes the semi-metal silicon and produces what we know as sand. So silicon dioxide, also known as silica, is an oxide of silicon with the chemical formula SiO2, most commonly found in nature as quartz and in various living organisms. In many parts of the world, silica is the major constituent of sand. The formula of silicon dioxide is SiO2, silicon dioxide with a molar mass of 60.08 grams per mole. Its melting point is 3,110 degrees Fahrenheit, 1,710 degrees Celsius, with a density of 2.65 grams per centimeters cubed, and a boiling point of 4,046 degrees Fahrenheit or 2,230 degrees Celsius. Silicon is found in the rock granite. Granite is a coarse-grained igneous rock composed mostly of quartz, alkali feldspar, and plagocase. It forms magma with a high content of silica and alkali metal oxides that slowly cool and solidifies underground. Sand, silicon dioxide or silica, and clay, aluminum silicate, are used to make concrete and cement. Concrete consists of the element silicon dioxide and calcium oxide. Another type of rock, it could be any type of rock that you find, you combine it with that, and then it combines to create cement, to create concrete, based on the proportions of silicon dioxide and calcium oxide, and the rock that you add depends on what type of concrete or cement you get. So silicon dioxide, when you add water to this, which is hydrogen and oxygen, as you can see, these form a relative amalgam, which is a combination or a fusion of a bunch of metals. So these are a bunch of rusty metals all together. Essentially, cement is rusty metals oxidizing with the carbon dioxide over time. When the concrete reacts with the carbon dioxide over time, it gets stronger, which is why Roman concrete is so strong, because it's had over 2,000 years to solidify and collect the carbon dioxide from the air. So returning back to silicon, granite and most other rocks are complex silicates, and these are used for civil engineering projects. So here we have the elements boron, gallium, arsenic, and phosphorus. Why do we have these elements here? Well, since we are talking about silicon and silicon is used to make silicon chips, we will talk about the step-by-step process later on in this video. But before we can talk about that, we need to talk about the various elements that are doped onto the silicon, which change its net energetic properties and allow us to use it as semiconductors, diodes, and transistors, which perform various functions in computer chips, in light bulbs, and in various other machinery that without we wouldn't be able to function the way that we currently do in our society. So boron has 3 valence electrons, gallium gallium also has 3 valence electrons. Arsenic and phosphorus differ from boron and gallium in that they have 5 valence electrons relative to the boron and gallium, which only have 3. And all compared to the silicon only has 4. So as you can see, we have a potential difference from 3 to 5. And that potential difference allows us to be able to create what we know as PN junctions or PNP junctions, which perform in transistors and diodes for us to be able to run electrical current that we know as electrons here, and allow us to be able to perform microscopic switches that turn off and on at the quantum level, essentially, and be able to compute various mathematical equations more quickly than we would be able to with just people alone. And that is what we call a computer. So the relative potential difference from the either arsenic or phosphorus and either boron or gallium create the potential to be able to create those transistors and PNP junctions with the silicon, which we will talk about shortly. So most of the silicon is used to make alloys including aluminum silicon and ferrosilicon, which is iron silicon. These are used to make dynamo and transformer plates, engine blocks, cylinder heads, machine tools, and to deoxidize steel, which is very essential. Steel needs to be deoxidized in order to remain strong and perform its function well. So silicon is one of the most useful elements to mankind, again considering that we use it to make computers which run everything that we do today. Without silicon, we would still be essentially in the Dark Ages. We would be back in the Renaissance 1,000 years ago. A fun fact that deviates from silicon is that a neodymium magnet or a permanent magnet consists of the elements neodymium, iron, and boron. Since we are talking about the elements boron, I just thought it would be an interesting fact to include it. So the elements neodymium are used in speakers, in tanning booths, and in laser surgery. Alloys of neodymium, iron, and boron make the magnets in microphones, headphones, and speakers, which are all included in modern-day smartphones and computers, which are also included with the silicon chips that we are mentioning today. So it's another element that's useful along with the silicon in today's devices. Iron, another very useful element. Blood's red color is from the iron in hemoglobin, which helps carry oxygen from the lungs to cells. The red planet, Mars. The surface of Mars appears red due to iron oxide, more commonly referred to as rust. The Earth's core is 80 to 85% iron. Movement of molten iron in the outer core generates a magnetic field, which is why we have compasses that are always pointing north, because of the magnetic field that is generated from the iron core that is constantly flowing within the Earth, generating electron flow and inducing that magnetic field, causing the needle to point north and allowing you to not get lost. Continuing on with boron, previously mentioned, borax sodium tetraborate is used as a preservative and buffer in eye drops and contact lens solutions. Boron is used in pyrotechnic flares to give them a distinctive green color. Boron trioxide is used to manufacture heat-resistant borosilicate glass used for laboratory glassware. Continuing on from the deviation, silicon is used to make transformer plates and engine blocks. Shown here, transformer plates are used to increase or decrease voltage, called a step-up or step-down transformer. Here is an image of an engine block, and so as previously mentioned, things that get very hot need to be able to withstand and remain the same shape and the same metallic composition that they were previously, before and after use and during use, and silicon is one of those metals that's used, along with tungsten, which we will eventually talk about in another video. So the element silicon is also used to make silicones. These are silicone oxygen polymers with methyl groups attached. They have various properties and people use them for various functions, and they even apply them to their bodies occasionally. So here's the element silicon with an R group. So an R group, an abbreviation for any group in which a carbon or hydrogen atom is attached to the rest of the molecule. R is an abbreviation for radical, when the term radical applied to a portion of a complex molecule, not necessarily a free radical, such as a methyl group. So illustrated glossary of organic chemistry, R group. That was a definition of that. And here is the R group, which is why we mentioned it. And here is the silicon oxide bonds that are made. They're bonded together. Silicon oil images are presented here. Here we have functional groups. We have hydroxyls, we have methyl groups, carbonyl, carboxyl, amino, and phosphate. Hydroxyls, quick review, they have an R group, an oxygen, and a hydrogen. A methyl group has an R group, a carbon, and 3 hydrogens. A carbonyl has a carbon, 2 R groups, and 1 R prime group, along with 1 carbon and 1 oxygen. Carboxyl with 1 hydrogen, 1 R group, 1 oxygen, and 1 hydroxide group. An amino group with 1 R group, 1 nitrogen, hydrogen and 2 hydrogens, a phosphate with 1 phosphorus, 2 hydroxides, 2 oxygens, 1 double bonded and 1 single bonded, along with an R group as previously mentioned. An R group is simply an abbreviation for any group in which a carbon or hydrogen atom is attached to the rest of the molecule. So an R group can be carbon or hydrogen. That's it. Silicone rubber is used as a waterproof sealant in bathrooms and around windows, pipes, and roofs. So here are the images. Here are the restrooms. Here are the roofs. And here are the pipes that silicone rubber could potentially seal. So if you have silicone rubber, you can use it to seal those locations along your house. So granite is the typical type of plutonic rock. It consists of feldspar, quartz, and a few dark colored minerals. I previously talked about granite, but I didn't specifically describe the elements, so we'll go into that right now. So the main chemical proposition of the granite are silicon dioxide, so that's why we're talking about granite. So 65% to 70% silicon dioxide and a little of aluminum oxide, Al2O3, calcium oxide, magnesium oxide, and iron oxide. A correction to the concrete, it's not calcium dioxide, it's calcium oxide. That's it. So granite essentially consists of the elements aluminum, oxygen, calcium, magnesium, iron, and silicon. So when all of these elements combine together, you get granite. Don't take that knowledge for granted. Alright, so continuing on with the previously mentioned elements. Arsenic is an infamous poison and earned the name inheritance powder for its use for murder. Arsenic wood, chromated copper arsenate, is used to treat timber, with the arsenic imparting insecticidal properties. Poultry feed. Organic arsenic was formerly used in poultry feed to prevent infection and promote weight gain. Gallium. These are a little more difficult to read, but I'll read them for you. So gallium melting. Gallium's low melting point, 29.8 degrees Celsius, means that if you hold a lump of it, the heat from your hand melts it. Solar cells. Gallium arsenide converts solar energy into electrical energy and was used in the Mars rover cells. Technology. Gallium nitride GAN lasers, read from Blu-ray discs, GAN LED backlight TVs, laptop, and phone displays. Continuing on with phosphorus. Phosphorus is in DNA. Phosphorus is essential for life, and it forms part of the sugar phosphate backbone of DNA and RNA. So phosphorus matchboxes. Red phosphorus is found on the striking surface of safety matchboxes, which ignites matches when struck. So phosphorus light bearer. White phosphorus glows when exposed to oxygen. Its name is derived from the Greek for light bearer. Boron was previously discussed along with the neodymium magnets. So here it is, quick review if you want to see it again, but I already went over it. So if you want to review that again, then you can go back in the video, but let's continue. Quick review. A silicon is used for dynamo plates. Here is the commutator, which makes contact with the varying electrical voltages, the armature, which allows the thing to turn, the pivot bolt, which keeps everything in place, the adjuster strap bolt, another bolt that keeps everything in place, and the string-loaded brush holders are placed one on each side of the commutators. That's to provide tension for everything to make contact continuously. So let's take a look at the people that work with silicon on a daily basis and how they work it to create the devices that we use, such as this device that I'm using to create this video. Let's continue. So silicon is selectively doped with tiny amounts of boron, gallium, phosphorus, or arsenic to control its electrical properties, as previously mentioned. A solid-state drive is a solid-state storage device that uses integrated circuit assemblies to store data persistently, typically using flash memory and functioning as secondary storage in the hierarchy of computer storage. So the way a solid-state drive works is by inducing voltages and keeping the voltage preserved, and then the computer analyzes the voltages that are preserved, and based on the voltages that are either kept or not kept, it interprets the either voltage on or voltage off as either a 1 or a 0 respectively. It interprets that as various things based on the varying voltages. You can create different types of numbers in various groups that allow the solid state drive to store a lot of information in a small amount of space. All of that is done with silicon with electrical voltages. The computer reads off the zeros and ones, and based on that it recreates the information that was stored, and that's how computers communicate with each other, with zeros and ones. We communicate with words, which we interpret as ideas and other things in our minds, but computers communicate with numbers. The element silicon is used extensively as a semiconductor in solid state devices, SSD, in the computer and microelectronics industries. This is a pure crystal of silicon. This is what's used to make the silicon chips. Without the pure crystal, we wouldn't be able to make the silicon chips because because normally silicon is a crystal, but in fractured crystals within the same chunk of silicon rock that it is. So in order to get the silicon crystals and to get the silicon wafers, we need to crystallize everything, get it into a pure crystal, and then cut up the crystal and then shape each individual unit of that one crystal one by one to create the various chips. So for this, the silicon is selectively doped with tiny amounts of boron, gallium, phosphorus, or arsenic to control its electrical property. Let's continue. So I took notes on the whole silicon process and how it's purified and how it's made. So here we go. We're going to start with the whole process. So here we have silicon dioxide being combined with aluminum. So here's the molecular formula to produce silicon and aluminum oxide. Here's silicon dioxide combined with carbon to produce carbon monoxide and silicon. So those are one of the few ways that you can create silicon. So how is silicon made? How was it made back then? How is it made today? So elemental silicon is produced commercially by the reduction of silica. So SiO2 with coke in an electric furnace. An impure product is then refined. So on a small scale, silicon can be obtained from the oxide SiO2 by reduction with aluminum. So you can see here, as previously discussed, you can create silicon by reducing it with unoxidized aluminum. So this is from a video on YouTube, and I extracted these photographs to make it easier to follow along with the silicon making process that I also learned about. So how do you make monocrystalline and multicrystalline silicon according to the video? So here we have an example of monocrystalline and multicrystalline silicon. The difference between monocrystalline silicon and multicrystalline silicon is that monocrystalline silicon is all one unit, it's all one crystal, and it's useful to make silicon wafers. We can't make silicon wafers or chips if we have multicrystalline silicons. We use that for other things, but we need monocrystalline silicon to make silicon chips. So how do we do that? Processing of silicon. So quartzite. Silicon is essentially quartz. The sand that you find at the beach is quartz, silicon dioxide. So we need to turn quartzite into metallurgical silicon. So the source of silicon is quartzite. So how do you make the silicon material pure and how is it processed? So we're going to go over that step by step. So step 1, the quartzite is placed into a furnace. Step 2, it's heated up to a temperature of 1900 degrees Celsius. Step 3, molten quartzite is mixed with carbon. Step 4, carbon is a mixture of coal, coke, and wood chips. So step 5, the carbon reacts with the silicon dioxide as carbon monoxide. The equation goes as follows. Carbon monoxide combined with silicon dioxide produces silicon with carbon dioxide gas. So the balanced equation is 2 moles of carbon monoxide combined with 1 mole of silicon dioxide produce 1 mole of silicon and 2 moles of carbon dioxide. So what is an electro arc furnace? Because this is what's used to produce the silicon as it's melted and stuff. So an electric arc furnace is a furnace that heats charged materials by means of an electric arc. Industrial arc furnaces range in size from small units of approximately 1 ton capacity up to about 400 ton units used for secondary steelmaking. So its useful life is 20 to 30 years according to consumer.ca. So it's molten silicon. Molten silicon is extracted from the arc furnace. The reactions that we previously discussed took place and now we have molten pure silicon. So how do we process that and how do we create silicon chips exactly? Let's get into that. So fun fact about the quartzite previously where we extract the silicon. So it's oxidized by oxygen. It's a rock of pure rusty silicon. So sand is just essentially rusty silicon. When you go to the beach or when you go to the desert or when you encounter a location that has a lot of sand, know that that's metal that's rusty and it's actually silicon. Although it may not look like metal like most rocks do in their ore form, it's still a metal. So yes, there's actually oxygen gas in there as there is in all rusty metals. So when purified, the O2 is removed and the rock will be lighter. So that's why it's actually called reduced when something regains its electrons because it's losing oxygen in the process and it's regaining its electrons. It's being reduced in weight. Previously, when they used to create metal ores by removing the oxygen from the metal, they would weigh the metal ore before and after and they would notice that it's lighter than before. So they would call it a reduction. And that's why, because the oxygen is now in the air. It's no longer in rock form. So continuing on, I was gonna do a contest where you guys can vote, but I already explained it, so there's no need for the contest. We'll do that in another video. So what is an integrated circuit? Because that's what we need to make with the silicon. So an integrated circuit or monolithic integrated circuit is a set of electronic circuits on one small flat piece of semiconductor material, usually silicon. Large numbers of tiny MOSFETs integrate into a small chip, according to Wikipedia. Its invention date is April 25, 1961, according to PBS.org. So let's continue. 70% of of silicon is used in the aluminum casting industry, as previously mentioned, because silicon can resist high temperatures and engine blocks consist of aluminum. Because of that reason, they reach high temperatures and they need to sustain those high temperatures without breaking the frame. So the aluminum silicon alloy is essential for high thermal resistance materials. So the other 30% is used to make chemical products like silicones, and surprisingly, what we associate silicon for the most is actually the thing that it's used for the least. So less than 1% of the silicon is used for electronics, and even though it's 1%, it's still a complex process that requires a lot of energy, a lot of work. So that 1% extracts a lot of energy from the world itself. So the processing of silicon. So how do we get metallurgical silicon to polycrystalline silicon? But first we're going to go over this molecule. So here we have trichlorosilane, and the reason I mention it is because it will be mentioned further on in the video. Trichlorosilane is a compound of silicon combined with hydrochloric acid. So the reason we need to do that is in order to create the crystals and crystallize them. We'll talk about that in further detail. So trichlorosilane is this compound right here. So let's talk about that. Trichlorosilane is an inorganic compound with the formula HCl3Si. It is a colorless volatile liquid. Purified trichlorosilane is the principal precursor to ultra-pure silicon in the semiconductor industry. In water, it rapidly decomposes to produce a silicon polymer while giving off hydrochloric acid, according to Wikipedia. Its molar mass is 135.45 grams per mole. Its boiling point is 89.24 degrees Fahrenheit or 31.8 degrees Celsius. Its density is 1.34 grams per centimeters cubed. Its formula is HCl3Si. Its melting point is negative 195.9 degrees Fahrenheit or negative 126.6 degrees Celsius. It's only soluble in water through hydrolysis. So let's continue. The reason I mentioned that is because we will mention this molecule shortly. So continuing on with these steps. Step number 6, the oxygen is leaving the furnace as carbon monoxide and carbon dioxide. And step number 7, the molten silicon that is formed is drawn out of the furnace and solidified. So here we have that image as previously discussed. And step number 8, the purity of the solidified silicon is around 98 to 99%, which is as close as we can get to in real life. Because in the ideal real world, nothing is ever 100%. So the next level of purity is called polycrystalline silicon. So now that we have metallurgical silicon, we need to make polycrystalline silicon. And how do we do that? Let's continue with the process. So metallurgical silicon, talked about that. Metallurgical grade silicon. The silica is reduced, which means that the oxygen is removed, as again previously discussed, through a reaction with carbon in the form of coal, charcoal, and heating to 1500 to 2000 degrees Celsius in an electrode arc furnace. It is 98% pure and is used extensively in the metallurgical industry, according to pveducation.org, refining silicon. So powdered metallurgical silicon, here it is, it's combined. So metallurgical silicon, that's why we need to create the powdered metallurgical silicon first. Once we have the powdered metallurgical silicon, we create it with hydrochloric acid. I previously made a video discussing how to create hydrochloric acid. If you're interested, after you're done with this video, or you can watch it right now if you like, however you wish, you can click on the link in the description and you can go ahead and view that video to learn how to make hydrochloric acid. It's actually how to make aqua regia, but it includes the process for how to make hydrochloric acid in the video. So let's continue with hydrogen and chlorine. So hydrochloric acid is essentially hydrogen and chlorine. When it's combined with the silicon, it produces this molecule that we previously discussed. This is how it looks like in the three-dimensional realm. So it consists of one silicon atom bound to 3 atoms of chlorine and 1 atom of hydrogen. So again, as previously discussed in the hydrogen video, if you're interested in watching that, you can click on the link in the description below. I also made a video describing how chlorine works. We're currently learning about the properties of silicon, so let's continue. So silicon combines with chlorine and hydrogen to produce this three-dimensional molecule. A lot of molecules are three-dimensional, some are flat, but essentially everything has dimension if you zoom in enough. So elevated temperatures in the presence of a catalyst. So they insert a catalyst to allow the process to occur more easily. Quick review. Hydrochloric acid, also known as muriatic acid, is an aqueous solution of hydrogen chloride. It is a colorless solution with a distinctive pungent smell. It is classified as a strong acid. It is composed of the gastric acid in the digestive system of most animal species, including humans. Its formula is HCl. Its molar mass is 36.458 grams per mole. Its boiling point is concentration dependent. Its melting point is also concentration dependent. Its pH level is 3.01, according to aqion.de. So let's continue. Step 1. The SiHCl3 trichlorosilane gas is cooled and liquefied. Step 2. Impurities with higher or lower boiling points are then removed using distillation. Step 3. Purified SiHCl3 is evaporized again in a different reactor and then mixed with hydrogen H2 gas, a metal. By the way, this process is called the Siemens process. It's a process used to create semiconductor grade silicon. It consists of heating metallurgical silicon to 300 degrees Celsius in a current of hydrochloric acid gas in a fluidized bed reactor to form SiHCl3. So the reactor reaction goes as follows. 1 mole of solid metallurgical silicon combines with 3 moles of hydrochloric acid gas. At 300 degrees, it's heated up and it produces trichlorosilane and hydrogen. So more details about the Siemens process. So the Siemens process involves deposition of silicon from a mixture of purified silane or trichlorosilane (TCS) gas with an excess of hydrogen onto high purity polysilicon filaments. The silicon growth then occurs inside an insulated reaction chamber or bell jar, which contains the gases. This is called the Siemens process, and this process consumes a lot of energy. So silane is liquefied and distilled and then reused. We need to reuse everything because everything is made out of molecules, and molecules can be reused essentially. So step 1, step 2, step 3, and step 4 from this side. So silicon atoms start to condense on the metal rod, and that's what creates the purified silicon crystals that we need. This deposition method is called chemical vapor deposition. So silanes and hydrogen are still an exhaust gas, so these gases are recycled and used again. So people also ask, what is the name of the most common process by which monocrystalline silicon ingots are made? So the crystal growth process. The monocrystalline silicon ingot from which silicon wafers are created are manufactured by a technique called the Czochralski crystal growth process. It's a monocrystalline pulling process. In an alternative fluid bath reactor method, only 1 out of 1 million atoms isn't silicon within the crystal. So that's really pure. We take gases, the silicon melts, and then we use that to remove the impurity. So this method is not as effective as the previous methods, but it still works. So let's learn about how wafers are made. Here's just a quick image about silicon. This is an app that I bought, so it describes a lot of chemistry and a lot of chemicals, and silicon is one of the many descriptions that it presents. So synonyms and trade names. Elemental silicon. Note, does not occur freely in nature, but is found in silicon dioxide, silica, and in various silicates. Its formula is Si. Its exposure limits are presented here. Its measurement methods. Physical description is black to gray, lustrous, needle-like crystal. Note, the amorphous form is a dark brown powder. Incompatibilities and reactivities. So it reacts with chlorine, fluorine, oxidizers, calcium, cesium, carbide, and alkaline carbonates. Its exposure routes are inhalation, ingestion, skin, and or eye contact. Its symptoms are irritation to eyes, skin, upper respiratory system, and coughing. So its target organs are eye, skin, and respiratory system. So Jan Czochralski, he's a Polish chemist. Jan Czochralski was a Polish chemist who invented the Czochralski process, which is used for growing single crystals in the production of semiconductor wafers. It is still used in over 90% of all electronics in the world that use semiconductors. He is the most cited Polish scholar. So he was born on October 23, 1885 in Kępin, Poland. He died April 22, 1953 in Poznań, Poland. His spouse was Margit Haas. She was married 1810 to 1953 with him, and he is known for the Czochralski process. So here is an image of Poland. A fun fact about Poland is that there's actually an element named after the place, named by Marie Curie. Marie Curie is a Polish-French physicist. Marie Salomea Skłodowska-Curie, born Maria Salomona Skłodowska, was a Polish and naturalized French physicist and chemist who conducted pioneering research on radioactivity. According to Wikipedia, she was born November 7, 1867 in Warsaw, Poland, and she died July 4, 1934 in Passy, France. She discovered radium and polonium. Her children are presented here, and her education is the Sorbonne in 1903, University of Paris, 1894, University of Paris, 1891 and 1893, and Curie Institute and Flying University. Her quotes are, "Nothing in life is to be feared, it is only to be understood. Now is the time to understand more, so that we may fear less." Another quote is, "Be less curious about people and more curious about ideas." Her other quote is, "I was taught that the way of progress was neither swift nor easy." So let's continue. So Jan Czochralski, I'm going to try to say his name correctly. So this method was produced. So the solidified ingots are then sliced into thin wafers during a process called wafering. After post-wafering processing, the wafers are ready for use in fabrication. Compared to the casting of polycrystalline ingots, the production of monocrystalline ingots is very slow and expensive. So let's see just how slow and expensive it is. So step number 1, a method to grow single crystal silicon. Highly purified silicon is melted in a crucible at typical temperatures of 1500 degrees Celsius. So it's usually doped with boron or phosphorus because boron has a +3 charge and phosphorus has a +5 charge, and that causes a relative potential difference for the transistors that we are trying to build within the semiconductor itself, which is why we're actually using the silicon, because it can be doped with other elements that give it a potential different charge on the same crystal. So this can be intentionally added to make p-doped and n-doped silicon respectively. So step 2, a seed crystal that is mounted on the rotating shaft is dipped into the molten silicon. So it's like Step number 3, the seed crystal's orientation is well defined, being either a 100 orientation or a 111 orientation. So step number 4, the melt solidifies at the seed crystal and adopts the orientation. So this single orientation is crucial for the production of silicon chips. So the crucible is made from quartz, which partially dissolves in the mold as well, resulting in a high O2 level. So we don't want a high O2 level because that creates rusty silicon for us. And that gets us back to square one. This is step 5 and 6. Here we have the crystal that was being extracted thanks to the orientation that was pre-selected. So usually the silicon is encapsulated with a noble gas such as argon. If you're interested in watching the video for argon, the link is in the description below. Argon is a chemical element with the symbol Ar and atomic number 18. It is in group 18 of the periodic table and is a noble gas. Argon is the third most abundant gas in the Earth's atmosphere at 0.934%. According to Wikipedia, its symbol is Ar, its atomic mass is 39.948, its atomic number is 18, and its electron configuration is neon 3s2, 3p6, its electrons per shell is 288, its boiling point is negative 302.5 degrees Fahrenheit or negative 185.8 degrees Celsius. So the texture and smoothness. The processing of silicon from a polysilicon crystal to a silicon ingot, which is way more shiny and way more cool looking. Poly means many and mono means one. So here's carbon and oxygen, two elements that are fundamental in the silicon making process. So the second method for producing monocrystalline silicon is called the float zone process. This results in monocrystalline silicon ingots with extreme low densities and impurities like oxygen and carbon. So here we have the X-ray vision of how it's created. So induced crystallization via heat transfer. So step number 1, the source material is a polycrystalline rod as processed in the earlier mentioned Siemens process. So step number 2, the end of the rod is heated up and melted using a radio frequent heating core. Step number 3, the melted part is put in contact with seed crystals. Step number 4, here it solidifies again and adopts the orientation of the seed crystal. Step number 5, both 100 and 111 orientations are being used. Step number 6, many impurities remain and move along the molten zone like a tube of toothpaste. Step number 7, nowadays during the process, nitrogen is added, which improves the control on micro defects and improves the mechanical strength of the wafers. Step number 8, the advantage of the float zone process technique is that polysilicon/monosilicon does not come in contact with the quartz, the silicon dioxide as previously mentioned, which is what gets us back to step 1, reducing potential oxygen impurities. So step number 9, the silicon only comes in contact with elements like argon, previously mentioned, a noble gas that does not react with anything. So step number 10, diboron and phosphine gases can be added to dope the silicon with phosphorus and boron. So that's just a creative way to dope the silicon, creating a p-doped and n-doped silicon that will eventually be cut into wafers for transistors. So the Krokoski method is the most important method for the production of bulk single crystals of a wide range of electronic and optical materials. Then the seed is slowly withdrawn from the melt, often under rotation, and the melt crystallizes at the interface by forming a new crystal portion. So this is in contrast to the images. Here we can see that silicon is being purified by this ring as it's being dragged up like a tube of toothpaste, and it creates that silicon. So the processing of silicon from ingot to multicrystalline ingot. So multicrystalline silicon can be produced as well. So step number 1, melting high purified silicon in a dedicated crucible. So step number 2, pour molten silicon in a cubic shaped growth crucible. Step number 3, here the molten silicon solidifies into multicrystalline ingots. This process is called silicon casting. Step number 4, directional solidification. This happens if melting and solidification occurs in the same crucible. So the cross section can go up to 70 by 70 centimeters once wafers are cut, and the height is typically 25 centimeters. So what is a diode? A diode is also similar to a transistor in that it can act as a conductor or an insulator based on what you need it to do and based on what orientation you position it in. So if you position a diode as a forward bias, it acts as a conductor, and if you position it as a reverse bias, it acts as an insulator. So this is according to the engineering mindset. If you want to subscribe to them, go ahead and look them up on YouTube, or I can leave a link in the description if I remember to do it. Other than that, this is the diagram that they presented, and thanks to their help, you can understand better how diodes work. So if you're interested in checking out that video, go ahead and check out that video and go learn about how diodes work so you can appreciate silicon even more. So a power inverter. A power inverter or inverter is a power electronic device or circuitry that changes direct current to alternating current. The resulting AC frequency obtained depends on the particular device employed. I previously bought a lead acid battery power inverter, but I drained it and now it's not working. The reason I mentioned that is because power inverters use transistors in order to work, and transistors are made of silicon. Transistors are used for inverters, silicon is used for this, so it all connects. What is a transistor, you may ask? So a transistor is a semiconductor device used to amplify or switch electronic signals and electrical power. Transistors are one of the basic building blocks of modern electronics. It is composed of semiconductor material, usually with at least 3 terminals for connection to an external circuit, according to Wikipedia. And these are some images of transistors. So once we have the wafers, we cut them up and we divide them so that we can create individual chips. So those wafers aren't the chips, they are the plates where multiple chips will be created and then cut up. So here is how that looks. This is the whole monocrystalline ingot, and it's cut into a lot of wafers. So now we know how to produce monocrystalline and multicrystalline ingots, but how do we make wafers out of them? So we do that by sawing. The disadvantage is that we lose a significant amount of silicon as a curve loss, but that's okay because when we cut something up, we have to accept the loss in between that cut. It happens for wood, it happens for metal, and it happens for this case silicon wafers. So the thickness of the wafers can range from 150 to 200 microns in the sawing and the polishing process. The thickness is usually determined by the wire or the saw cutting that's cutting the silicon. So this is cut in order of hundreds of microns of silicon. So sawing will logically damage the surface of the wafers, so they are polished. That's an important step, by the way. So silicon ribbon is a completely different approach to making wafers. So it's based on a high temperature resistant string. As silicon solidifies on string sheet of silicon, which is crystalline, it's pulled out of the melt. The ribbon is cut into wafers. The reason this step is very effective is because it does not include a sawing step, and that's very, very essential. So here's how the silicon wafers look before and after they're polished. So here we can see that they have rough edges on the sides, and they have like bunch of abrasive things because of the sawing, but afterwards they're polished and they're restored like a metal is when it's polished. So the surface is further treated before turning into solar cells. So this process is used to create things like solar cells. The electronic quality is not as good as monocrystalline silicon, so that's why it's not as common. But again, the advantage of this method, the ribbon method, is that you don't need to saw it. So let's continue with the element silicon. So continuing on with silicon, we're going to take a look at the individual steps that are taken after the wafers are cut. So the individual chips are usually sawed out of the wafer. The line which is cut is called the scribe line. So it's the space between the chips that is reserved to saw. So depending on the size and the type of the chip, the wafer will now contain anything from several dozen to thousands of chips. So step number 1, the residue has been stripped, the wafer has been cleaned. Step number 2, the wafer undergoes further oxidation. Step number 3, it's electrically conductive. This is the oxidation layer, so they put on an oxidation layer. The polysilicon is deposited. Step number 4, photoresist is applied again. Step number 5, this little sheet of glass, this little strip is to prevent the light from chemically changing the photoresist. So continuing on. Step number 6 is light exposure. As you can see, there's a differentiation between the lighted area and the non-lighted area. So this is the non-lighted area and this is the lighted area. So continuing on, step number 7, the exposed region, the area shielded from the light, is now still yellow as before, and the exposed region is now red. As you can see here, the red was already previously below and it was just altered. So step number 8, polysilicon and oxide remain. The layers are etched off. Step number 9, they remain intact, the center, the 2 layers. Step number 10, oxide layers applied. Step number 11, the wafer undergoes another cycle of applying photoresist and then applying the light, so bright light exposure. As you can see, the red arrows point to it right here. This is what's going to be etched. And step number 13, the result. Step number 14, contact holes are stripped to provide access to the conductive layers, seen here. Step number 14.5, that's how it looks like. Step number 14.6, photoresist and mask are applied. Step number 15, once again, the photoresist and mask are applied. Step number 16, the unexposed strips remain as is. Step number 17, the unexposed strips remain as is after the etching process. And this is the light beam again, and this is the coverings for the light. Step number 18.5, that's the result. Step number 18.51, providing a point of contact for underlying layers. There it is. As you can see here, it's not lined up flush because tiny parts of the wafer splinter off during the sawing process. Test structures are also integrated in the space between the chips and used to take measurements immediately after production. These are destroyed in the sawing process. So metal alloys are attached to the wafer in sputtering machines, and everything is washed with special chemicals to remove dust and debris from fabrication. So these steps are repeated until the chips are completed. So even though they're just presented in a series of steps, they're repeated until everything is completed within the chip. And that all depends on the manufacturing design of the company or the producers of the chip and the product that they want. So that was silicon explained in 60 minutes or less. If you're interested in watching the previous video, it's on nuclear power explained in 11 minutes or less. The next element will be on arsenic. If you guys like this video, make sure to like, comment, subscribe as always. Thank you guys for watching. Have a great one.